All right, so let's have a little example of a what's called a non-constructive proof, just for fun. Okay, so this doesn't actually use anything past algebra 2, right? Okay, so here's our little theorem. There exists a pair of irrational numbers. So numbers in R less Q, right? And I'll call those numbers, say, x and y, with x to the y is in Q. Cool? You guys understand what I mean by this? Okay, so one, why is this interesting at all?
You're saying that there exists two rational numbers, and when you put one to the other, it's rational.
Yeah, two irrational numbers where one raised to the other is rational again.
Oh.
That would be something like this, right? That would be something like maybe pi to the e is 7/4 or something. Like, that should feel a little odd, right?
Mm-hmm.
You guys see what's kind of strange there?
Mm-hmm.
And also, like, R less Q is so much bigger than Q, right? That if you slam a couple of these things together, it seems like there should be like virtually no chance of landing in Q. You guys pull that?
Is it that much bigger?
Yeah. Yeah, this thing is uncountable. That thing is countable.
Oh, you're right.
There are only as many things in here as there are counting numbers, right, in Q. But there are uncountably many of these, which means that even if you had one of these sets for every number in the counting numbers, you still wouldn't get to this size. You guys cool with that? So this is a little strange. Right? Okay, but this thing's not constructive, so I'm not going to find out that this is pi to the e is 7/4. I'm going to do this slightly strange thing, where I'm going to take the square root of 2, which is irrational, right?
Mm-hmm.
And then I'm going to raise that thing to the square root of 2 power. You guys good with this?
I mean, yeah, definitely.
I mean, this is just like me starting someplace. Like, this is the classic prove or give a counterexample. I don't freaking know. I don't know any tools, so I'm just going to start somewhere and see if I can like fiddle with this. So I started with the two simplest irrational numbers I know. The fact that they're the same number makes them definitely simple, right? Okay, so this is a little weird, but the only thing I know about this is that either it's irrational or it isn't, right? You guys see that?
Mm-hmm.
Okay, so I'm going to call this thing x. And there's only two options. On the one hand, x might be in Q. If that was true, where would I be with this claim?
You proved it.
True.
Yeah, then I've provided the existence of a pair of numbers, right? If this, then done. Right? So that means the only other interesting case to me is what if not, right? So if x is in R less Q, then what?
Inconclusive.
Then that thing's irrational.
Then that thing's irrational, right? So then we're going to consider, actually let me write up here for, oh, Kenny's not here. Kenny's not here. So let's just consider anyway, x raised to the square root of 2 power. What's that? That's the square root of 2 to the square root of 2 raised to the square root of 2. Right? which gives me
2.
2, which is a
Rational number.
fraction, right? So there's no 2 options on that one, right? That one's in Q. But what's the weird thing here?
I see where you're going with this. Either it's true or it's true.
Yeah, so I'm done, right? Because either the pair of numbers is the square root of 2 and the square root of 2, or the pair of numbers is the square root of 2, the square root of raised to the square root of 2, and the square root of 2.
That is freaking hilarious.
You guys see that? You know which one it is?
Probably the second one.
All right. I have no idea.
Oh, well, that's not the point of this, though.
Yeah, that's not the point. I'm done either way. But I haven't told you which pair it is, and I don't actually know. Don't tell me, by the way. If you look this up, I do not want to know, because one of the coolest things about this to me is that I don't know which pair it is. If I know, it'll take all the fun out of it. You guys cool with this? So this is strange, right? This is some of the flavor of a class called number theory. Cool?
I mean,
Number theory is funky because every time you do a proof in number theory land, you don't know any friggin' thing. Like most number theory proofs, you don't know anything more than like algebra 1. But you can still prove stuff. It's crazy. So,
I'm not really understanding how that actually proves something by just putting it to the square root of 2.
Because even if it's not rational on the left-hand side, it becomes rational on the right-hand side.
so I have 2 options, right? So ultimately, I have either square root of 2 to the square root of 2, right, is rational. Oops, is. Or square root of 2 to the square root of 2 to the square root of 2 is rational. Right? And this is one irrational number raised to another irrational number. And I don't actually know whether this number is irrational or not, but I know that if I raise it to this irrational power, I get an irrational number out. Right? And so in the end here, I have one of these 2 pairs, right? Either square root of 2 square root of 2 is the pair you're looking for, or square root of 2 to the square root of 2 and square root of 2 is the pair you're looking for. I don't know which one it is, but it's one of those pairs. Cool with it? And I'm really just exhibiting this, right? I'm not saying that every pair of irrational numbers has this property. I'm just saying there exists one. I still don't know which one it is, and I don't want to know. But one of those 2 is a pair like this. Cool with that?
kinda, yes.
Kinda, yes.